Types of chemical reactions in solution stoichiometry. Another quick review before we head into the really tough stuff. At the end of the year in pre-AP chemistry, we talked about solutions. You even made a few blue solutions of your own. And I'm going to do a quick recap on some of the terminology. Two words you should be familiar with are solute and solvent. Solute is what gets dissolved. It's typically some type of salt, and solvent is what does the dissolving. For our intent and purposes, our solvent is almost always water. So how does a solution work? Well, we take a solute, some kind of salt. We used copper sulfate last year. Copper sulfate is that blue salt that you saw in your virtual lab last week as well. We're going to add water to it to dissolve said salt, and we get a solution. So a solution is anytime I dissolve a solute into a solvent, and voila, now we're ready to begin. Water is known as a common solvent. It can dissolve pretty much anything. For one, it has a very high specific heat. That means it requires a lot of heat in order to raise its temperature by a simple 1 degree Celsius. That's why water remains in the liquid form as opposed to turning into water vapor. If you think about the ocean, you have the sun beating down on the water all day long, even in the middle of summer, but it still remains as a liquid. It requires a lot of heat to be absorbed in order to change it from a liquid to a gas, which is a definition of heat of vaporization. Vaporization, I'm going from liquid to a gas. So because water has a high heat of vaporization, it remains in the liquid form as opposed to the gaseous form. It also has high cohesive and adhesive forces. Cohesive meaning the water particles stick to each other, and adhesive forces meaning the water particles readily stick to other substances. All of these properties contribute to life on this planet, with the most important, in my opinion, being the high specific heat. Now let's look at the actual water molecule itself. We have oxygen here in the middle. We have 2 oxygen-hydrogen bonds, and I have 2 sets of valence electrons, 2 lone pairs here around the oxygen atom. So let's look at these 2 oxygen-hydrogen bonds. We say that they are polar covalent. Covalent because oxygen and hydrogen are sharing their electrons, and polar because that sharing is unequal. Why the unequal sharing? Well, oxygen has a higher electronegativity. If you've forgotten this word from Chem 1, I'm going to encourage you to write it down now. Electronegativity is the ability to attract electrons within a molecule. Let's take a look at the periodic table and let's compare the electronegativity of oxygen and hydrogen. We know, hopefully, that as we move from left to right, electronegativity increases. Ability to attract valence electrons increases. So what part of the atom itself is responsible for attracting those valence electrons? And hopefully you've all shouted out with pride that it's the nucleus. The highly positive nucleus on the inside of an atom is responsible for attracting those valence shells of electrons. So how many protons are in the nucleus of a hydrogen atom? And if you look at its atomic number, 1, that tells me it has 1 proton inside of its nucleus, and oxygen has 8 protons inside of its nucleus. So if I'm comparing their nuclear strength, oxygen has more protons, which means it can pull those valence electrons in closer to its own nucleus. So back to our drawing. We have 2 polar covalent bonds between oxygen and hydrogen. Because oxygen is more electronegative, it pulls those electrons in closer to itself, the electrons that it's sharing with the oxygen. So as a result, we get a slightly negative oxygen end of the molecule and a slightly positive hydrogen end on the molecule. The unequal charge distribution makes the water molecule polar, which is very important once we get to solubility. And we also notice that there's this 105-degree bond angle. The bond angle is the result of two different things. The first being the two unshared electron pairs. So here's unshared electron pairs on the oxygen side of the molecule. We say that they are hogs. They require more space than shared pairs. Well, why do they require more space? I want you to think about the number of nuclei that are holding these electrons in place. The lone pairs around the oxygen atom are held in by one nucleus, whereas the valence electrons that are being shared between oxygen and hydrogen are being held in between two nuclei. That means the lone pairs around the oxygen atom have more space to roam, and as a result they squish the bond angle down to 105 degrees as opposed to the 109.5 that it should be. So why all the talk about its molecular geometry and bond angles and these partial charges that result in a polar molecule? Well, we know that opposites attract. The positive ends of a water molecule are greatly attracted to negative ions and vice versa. The negative ends of a water molecule or negative end of a water molecule is greatly attracted to the positive ions and a crystal structure. A common FRQ question on the AP exam has been to draw the attractions between water and ions. So we're going to take a really simple salt like sodium chloride, NaCl. And if we were to draw that, it would be a positive sodium ion, a negative chloride ion, and this would be a repeating pattern. And it would look like a crystal. Then we would have to draw in our water molecules, and let's do water in a different color so it kind of stands out. What we would want to do for this negative ion, it would be surrounded by the positive ends of a water molecule. Well, we know that the hydrogen end of the water molecule is a positive end, so I would draw the two hydrogens and then the oxygen atom on top, and it would be surrounded. There's another water molecule there, and we want the hydrogen ends facing the negative ion. We would also take this positive ion here. So if this positive ion is a sodium, I know that the negative part of the water molecule would be attracted to it. So I would draw the oxygen attracted to the positive ion and the two hydrogens on the opposite end. And you'll have to forgive my drawings here. I'm doing the best I can. Oxygen and hydrogens pointing in the opposite direction. So common FRQ question is to draw the attractions between water molecules. You did that in Chem 1. You should be very good at that by now. What exactly is solubility? Well, it's the ability to dissolve these ions in solution. Sodium chloride is highly soluble, but silver chloride is classified as insoluble. It does not dissolve. So how do we know when something is soluble and when something is not? Well, it depends on a few things. When the hydration attractions are greater than the crystal lattice or ion-to-ion attractions, the compound is soluble. So let's talk about energy and the types of attractions that are occurring between water molecules and ions. There are three types of attractions occurring within a solution. The first is ion-to-ion. Positive to negative ions are attracted one to another. The second is water to water. All water molecules are attracted one to another because they have those slightly positive and slightly negative ends. And the last attraction is between a water molecule and a charged ion. Ion-to-ion attractions, as seen here, are called crystal lattice attractions. Attractions between water molecules and ions are called hydration attractions. Now let's talk about these attractions in terms of energy. We need energy to break an ion-to-ion bond. We also need energy to break water-to-water attractions. But energy is released when I form new attractions between water molecules and negative ions and water molecules and positive ions. If the energy released from the new water to ion attractions, as seen on the right, is more than the energy that was used to break the ion-to-ion and water-to-water attractions on the left, then we have a soluble compound. But if the energy released by these attractions on the right-hand side, by these attractions here, if the energy released is less than the amount of energy that was used to break these attractions over here on the left-hand side, then we have an insoluble salt. So energy is the key to determining whether a salt will be soluble. Water can also dissolve non-ionic substances, covalent substances, which we call molecules, such as alcohols and sugars. And it can do that because alcohols and sugars contain an oxygen-hydrogen bond, and that oxygen-hydrogen bond is polar. So notice in these molecules here, in the ethanol, I have this oxygen-hydrogen bond. That oxygen-hydrogen bond results in a slightly negative and slightly positive end on this alcohol, and because it's polar, it means the water molecule, which is also polar, it has a slightly positive, slightly negative end, can be attracted to the molecule. So we have a positive, slightly positive hydrogen end on this ethanol, and we have a slightly negative end on the water molecule. Those partial charges are attracted one to another, and that means that water can dissolve this molecule. Fats do not dissolve in water because they are non-polar. They don't have any charges, not even partial charges, so water cannot dissolve fats. A good tip here, like dissolves like. It's a useful guide if you want to predict solubility, but it's not an explanation. If you are explaining why a substance is soluble or insoluble, you have to address those electrostatic aspects. You have to address the interactions between positive and negative charges. So as we stated on the first page, a solution is a mixture where a solute is dissolved in a solvent. An aqueous solution is when that solvent is water, and that's where we're going to focus most of our energy. So here's an example of an aqueous solution. We take a salt like barium chloride, we add it to water, the water molecules surround the positive and negative ions and break them apart. So we end up with an aqueous solution of barium chloride over here on the right. So what do we have floating around in our solution besides water molecules? Well, we have positive and negatively charged ions. If we consider the formula for barium chloride, BaCl2, that means that for every one barium ion, there are 2 chloride ions. So we have Ba2 plus ions and chloride ions that are floating around in my solution, charged ions. And this brings us to our first property. Electrolytes are solutions that conduct an electric current. The more mobile and charged particles present, so mobile means that they are moving around. I have to have a dissolved salt in order to conduct current. So if I were to put a conductivity meter on a bowl of salt, of just table salt, it wouldn't conduct electricity. Those salts would have to be dissolved in water, and those ions would have to be mobile. So I need mobile and charged particles. I need high concentrations of ions in solutions if I want to conduct a really good current. So that's simply more ions versus fewer ions. And last is magnitude. So we want ions that have greater charges, say a +2 versus a +1. An ion with a +2 charge will conduct a higher current than that with a +1 charge. Next is the word strong. A strong solution is one in where the ions completely dissociate, meaning they're completely broken apart. High solubility. And this refers to acids, bases, and salts as well. And acids and bases we'll spend a ton of time a little bit later on in the year, but we want to start now defining strong acids and bases as those that completely dissociate or break apart in solution. And let's take a look at our beakers above. And in this beaker, we have all positive and negative ions. Positive is hydrogen, negative is chlorine. So this is hydrochloric acid. Because it exists as mostly ions in solution, we would say that this acid is strong. So I'm going to put strong. And it's an acid because it begins with hydrogen, but more on that later. Now let's look at the neighboring beaker. It exists as mostly positive and negative ions, as all positive and negative ions. This NaOH is sodium hydroxide. It is strong because it's mostly ions in solution, and it's a base because it has that hydroxide ion. If I look at the beakers over here on the right-hand side, notice that they exist as mostly molecules because they're not broken apart. These little guys here, you see how they are still together? Because they haven't been dissociated or broken apart, we would call this weak. This is a combination of hydrogen, oxygen, and nitrogen. So this is a weak acid. Weak acid. And down here, I also see that my molecules have not been dissociated, so this would also be a weak solution. So to reiterate, barium chloride, this salt up here in my first set of beakers, is an ionic salt that completely ionizes in water. It forms barium ions and chloride ions in solution. HCl is a strong acid that completely dissociates into hydrogen ions and chloride ions in water, while sodium hydroxide is a strong base that completely dissociates into sodium ions and hydroxide ions. All three release mobile, charged particles that readily conduct electricity. Next are our common strong acids. You will have to memorize these, but I've got a little trick for you. We have 6 strong acids: hydrochloric, hydrobromic, hydroiodic, nitric acid, sulfuric acid, and perchloric acid. Let's check the periodic table and see where these acids are. We know that the acids are a combination of hydrogen, which we find all the way over here on the left-hand side of the periodic table, and an anion, a negatively charged ion. Well, our first 3 strong acids are hydrochloric, hydrobromic, and hydroiodic acid. So as far as memorizing them, you've got 3 right there in a row. It should make that pretty easy for you. Notice that all of group 7 is included except for fluorine. Recall that solubility has to do with the amount of energy needed to break the bonds between the ions and the water molecules and create new attractions between water molecules and those separated ions. So consider the size of fluorine, its electronegativity, and the amount of energy needed to break this HF bond. Fluorine is the most electronegative atom on the periodic table. It is going to require a high amount of energy to break the HF bond because of its electronegativity and because fluorine is a pretty small molecule. It has 9 protons and only 2 energy levels. Here's 1, 2 energy levels. So it's really small, it's really electronegative. We're going to have to use lots of energy to break that HF bond so it doesn't dissociate or break apart readily. As a result, it's not a strong acid. Don't be fooled, just because it's not strong doesn't mean it's not dangerous. As we move down this group with the chlorine, bromine, and iodine, the number of energy levels increase and the electronegativity decreases. That means the amount of energy needed to break apart the HCl bond, the HBr, and the HI bond is much less than that of the HF bond. So hydroiodic acid would be my strongest because it's the easiest to break apart. Okay, cleared that off. Now let's talk about our bases. Your strong bases will be any hydroxide, that's OH ion, any hydroxide that's bonded to a group 1 or group 2 metal. So if I have, say, lithium here, LiO, OH, that's considered a strong base. Same thing here. If I take that calcium, CaOH2, because calcium is +2 and hydroxide is -1, so I drop and swap, calcium hydroxide would be considered a strong base. There is one exception to this rule. So the only group 2 metal that is not considered a strong base when bonded to hydroxide is beryllium. And for the same reason that fluorine is considered a weak acid, because beryllium is really small, the amount of energy needed to break the beryllium hydroxide bond is really, really high, so it doesn't easily break apart or dissociate. It's considered a weak base. And to conclude, weak simply means that it does not completely dissociate. There's going to be some dissociation, some dissolving, but it's going to be very small. Everything dissolves a tiny, tiny bit. Even if we look at something and we say it doesn't dissolve at all, on the molecular scale, it is dissolving. So only about 1% or less is considered weak. Last thing before we move to the next page, I want you to be able to draw the following. What would it look like in a beaker? And you've got all the examples on this page. Can you draw an insoluble solid in solution? Can you draw a soluble salt as ions in solution? And can you draw strong acid versus weak acid and bases? What do they look like in solution? So this would be a soluble salt here. This one is soluble. These are your strong acid and base. They completely dissolve. They look like ions in solution. And these would be your weak acids and bases here. Also, if something is insoluble, what would it look like in solution? What would look like this one here? It wouldn't be dissolved at all. It would be a solid sitting at the bottom of the beaker. Moving right along, non-electrolytes are solutions where dissolving has occurred, but the solute does not make ions. Remember, charged particles. And because there's no charged particles, it cannot conduct electricity. Examples are pure water, sugar, alcohols, antifreeze, and starch. So these are all covalent molecules. And so even though they do dissolve, we end up with these chunks of molecules that don't have charges. And if there's no charge, then they can't conduct electricity. Arrhenius, you're going to hear his name throughout the year. He was the first to identify the conductive properties of solutions, and he correctly postulated that the extent to which a solution can conduct an electric current depends directly on the number of ions present. And we said this on the previous page, that the more ions we have in solution, the more conductivity for that particular solution. Let me give you a quick example. Let's compare sodium chloride and magnesium chloride, two soluble salts. When sodium chloride dissolves, it breaks apart into two ions, a sodium cation and a chloride anion, one of each. When magnesium chloride dissociates into solution, it dissociates into a magnesium 2+ ion and into 2 chloride ions. So over on this end, I get 3 ions in solution, and here I only have 2 ions in solution. So because there are 3 ions here versus 2 there, magnesium chloride would be able to conduct a higher current. All right, here comes some really important information, the composition of solutions. Chemical reactions often take place when two solutions are mixed. To perform stoichiometric calculations in such cases, two things must be known. The nature of the reaction, which depends on the exact substance and whether it exists as ions or molecules in solution. That's why knowing whether something is strong or weak is important. And number 2, the amount of chemical or the number of moles present in solution. In Chem 1, you were exposed to the term molarity, or big M, like you see here. Molarity is equal to moles of solute, the number of moles of that salt that I'm dissolving, divided by liters of solution. How much of a solution do I have? You have to be able to work with this formula, it's essentially what it is, and be able to solve for any of the variables. You should be able to solve for molarity, moles, or liters. And recall that we always list the variables, fill in what we know, and then rearrange our formula to solve for that missing unit. So molarity is nothing more than concentration. It tells us unit of moles per liter of solution. You'll notice that we're going to see brackets here, and we used them last year as well. Brackets tell us that whatever's inside of those brackets is A, a solution, and whatever number comes after it is its concentration expressed in molarity. So if I see brackets and then I see this 0.75, that means that there are 0.75 moles of sodium chloride and 1 liter of solution. And you'll see either the square brackets or the big M on the AP exam, and those both mean molarity. You'll also want to pay careful attention to this portion of our formula. Last week we used the term mole, and we said that moles are grams of a substance divided by its molar mass. So anywhere I have the term mole, I can replace it with the units gram divided by molar mass, and that's what you see being done here. I just want you to know that for stoichiometry, you can substitute those terms there. So now let's prepare some solutions of known concentration. We did this in pre-AP. At the end of the year last year, you made these blue copper sulfate solutions of different concentrations. For AP, you have to be able to explain how to make a specific molarity of solution, from the amount of solid that you need to the correct equipment, when to add what, and what to do at the very end. So step 1. We know that a solution is a solute, which is a solid, a salt in our case, that's dissolved in a liquid. So I need to know how much of that solid and how much total solution volume am I making. Step number 1, weigh out the solid. And step number 2, place it in a volumetric flask. You can see these steps being completed here. You have the solid in this person's hand. They're dumping the solid using a funnel into a volumetric flask. Step number 3, add only enough distilled water to dissolve the solid and swirl to completely dissolve this solid. And that's what's happening in picture number 2. A small amount of water has been added. You gently swirl that volumetric flask around until your solid completely dissolves, and now you're ready for step number 4. Then add a bit more water, filling to the mark on the flask. If you recall, or if you look at an actual volumetric flask, you're going to see that it has a line or a mark along the neck of the flask, and that line marks the particular volume for that flask. Some are 1 liter, some are 100 milliliter volumetric flask, some are 500 milliliter volumetric flask. So whatever the reading is on the flask itself, that one line it has on it represents the total volume. So quick recap. We've measured the amount of solid. We've added it to a volumetric flask of known volume. In this particular example, we're trying to make 1 liter of solution, so we've poured out our solid into a 1 liter volumetric flask. We've added a small amount of water to completely dissolve our salt, swirled it around, and then we carefully added water just until the mark on the neck of the volumetric flask. We put the cap, we shake, we make sure that our solid is completely dissolved. So quick question, Why wouldn't we simply fill the volumetric flask all the way to its mark, to the 1 liter mark here, and then add that masked out solid? Why can't we add the solid to 1 liter of solution and be done? Well, by adding the solid to 1 liter, we're neglecting the actual space that that solid would take or occupy in the solution itself. So it's not 1 liter of water, it's 1 liter of solution. So we have to ensure that we don't neglect the space that that solid would take up, and you can see the space that it's taking up here at the bottom of the picture. Because it's taking up some space in that flask, we can't fill it completely with 1 liter of water. Let's see if we can handle some practice calculations. We're going to follow the same systematic approach from Chem 1, where we underline what we have and put a box around what we need. Calculate the molarity, so I know I'm searching for molarity, of a solution prepared by dissolving 11.5 grams of solid sodium hydroxide and enough water to make 1.50 liters of solution. Since we've identified that we're solving for molarity, we're going to use the molarity formula. Molarity is equal to moles divided by liters. So step number 2, because we've identified our knowns and unknowns, that's step 1. Step number 2, we're going to list our variables and fill in what we know. Well, we weren't given number of moles of sodium hydroxide, but we were given 11.5 grams of sodium hydroxide. So we can use that to solve for number of moles. 11.5 grams of sodium hydroxide. And if I'm converting that to number of moles, that means I need to divide by molar mass of sodium hydroxide. And if I check the periodic table, sodium is 22.99. Oxygen is 16, and hydrogen is 1.01. Gives me a grand total of 40 grams per mole of sodium hydroxide. And if I round using 3 significant figures, 0.288 moles of sodium hydroxide. We're going to plug that in here. And our volume was 1.50 liters. We will plug into our molarity formula. Moles divided by liters. 0.288 moles divided by 1.50 liters. I need 3 significant figures, 0.192 molar. I'll give you a quick second to copy down anything you didn't get a chance to, but this question should have been fairly easy, and you should have been able to complete most of it probably without my help. Question 2. Calculate the molarity of a solution prepared by dissolving 1.56 grams of gaseous hydrochloric acid and enough water to make 26.8 milliliters of solution. Well, I'm going to save us a little bit of time. You're still going to follow the same format where you use the molarity formula, you list your variables. I'm solving for molarity, so this would be my question mark. I have 1.56 grams of HCl. I'm going to convert that to moles by dividing by the molar mass of hydrochloric acid. And then this says my volume is 26.8 milliliters. Notice that your unit is milliliters. We're going to convert that to liters by moving our decimal over 3 times, and we get 0.0268 liters. So you'd simply plug these numbers into the molarity equation. You'd round using, looks like 3 significant figures. And the correct answer, I'm going to let you work this one out on your own and check your answer, is 1.60 molar. Exercise 3. Give the concentration of each type of ion in the following solution. So concentration is molarity, molarity is moles per liter. So this wants to know how many moles of each type of ion are in the following solutions. If you're asked to find the concentration of each ion, we're simply going to multiply the ions by their subscripts to get how many there are in that solution. So let's do example A, and I'll let you do example B on your own. We have to find the concentration of cobalt ions in this 0.50 molar solution, as well as the concentration of nitrate ions in this 0.5 molar solution. So if we consider what it looks like in our beaker, we have cobalt 2 plus ions that are floating in solution, and we have nitrate ions that are floating around in solution. We want to know how many moles of each of those ions do we have per 1 liter of solution. Let's start with the cobalt ions first. If I have 0.5 molar cobalt nitrate solution, that's 0.50 moles of cobalt nitrate per 1 liter of solution. I just rewrote that molar as moles per liter. Now we're going to use a little bit of stoichiometry to convert molarity to number of moles of ions in solution. So for every 1 mole of cobalt nitrate, how many moles of cobalt ions are released? I see a subscript of 1 since there's nothing there. That means 1 mole of cobalt ions is released for every 1 mole of cobalt nitrate solution. Multiply across the top, divide by everything at the bottom, and my concentration of cobalt ions is the same as the concentration of solution, 0.50 molar cobalt ions. Now, simply by looking at the formula, can you determine what the concentration is of nitrate ions? Because for every 1 mole of cobalt nitrate, there are 2 nitrate ions, that means the concentration will be twice as high. For every 1 CO2 plus that's released, there are 2 nitrate ions that are released. So the concentration will be twice as much. I'm simply going to replace this with 2 moles of nitrate ions, and 0.5 times 2 would give me a concentration of 1 molar, 1.0 molar if I use 2 significant figures. And very important here at the bottom, always remember and never ever forget, this is a very nifty little tip or tool that you'll use, is that concentration and molarity times volume in liters is equal to moles. It's simply rearranging that formula. If I rearrange to solve for moles, I need to multiply concentration times volume times my liters. But very, very useful as we continue along this unit. Exercise number 4 asks us to calculate the number of moles of chloride ions, that's what I need, in 1.75 liters of 1 times 10 to the 3rd molar zinc chloride solution. So the first thing I want you to do is actually just picture what this looks like. Here's my container, it's a little beaker. Let's say that this beaker is holding 1.75 liters of solution. So there's my solution. The concentration of that solution is 1 times 10 to the negative 3rd zinc chloride. So check out your formula here. Check out the formula. For every 1 zinc ion that's dissolved in solution, there are 2 chloride ions that are dissolved in solution. 1 there, 1 there. Let's do another set just for good measure. For every 1 zinc, there are 2 chloride ions that are dissolved in solution. So here's my plan. I'm going to multiply my volume times my concentration to get number of moles of zinc chloride in solution, and then I'm going to convert my number of moles of zinc chloride to moles of chloride ions in solution. So let's move this out of the way here, and let's start with our plan. Let's multiply 1.75 liters of zinc chloride times the concentration, 1 times 10 to the negative third moles of zinc chloride per liter of zinc chloride. And the final step, I have moles of chloride on the top, so I need to have them on the bottom to get rid of them. For every 1 mole of zinc chloride, there are 2 moles of chloride ions. Check your units, make sure everything cancels that needs to. My liters of zinc chloride cancel, my moles of zinc chloride cancel, and I'm left with only moles of chloride ions. Multiply everything across the top, divide by everything you see on the bottom. How many significant figures? If I check back to the measurements in the problem, it looks like I have 2 significant figures there in that 1.0 times 10 to the negative third. I need 2 significant figures in my answer, 3.5 times 10 to the negative third moles of chloride ions. Put a box around your final answer and you're done. Option number 2 here is actually to take those variables just like we've done in the past, fill in what you know, 1 times 10 to the negative third liters, 1.75, and before you plug and chug and rearrange in this formula, you'd have to convert this 1 times 10 to the negative third moles of zinc chloride, or molar zinc chloride to molar chloride ions. Essentially, you're doing the same things. This stoichiometry just puts it all in one nice, neat package. Okay, exercise number 5. Let's move some of these things out of the way. All right, typical blood serum is about 0.14 molar sodium chloride. What volume, liters, of blood contains 1 milligram of sodium chloride? So if I'm going to answer this question with strictly stoichiometry, should I start my stoichiometry problem with 0.14 molar sodium chloride? Molar, again, is moles per liter. Or should I start it with this 1 milligram of sodium chloride? Well, remember I have to use conversion factors in stoichiometry. Which one of these units looks like it could possibly be a conversion factor? And hopefully you've circled this one. If I have numbers in that fraction, I can use it as a conversion factor. So we don't want to start with a conversion factor. We want to start with a unit that we have got to get rid of. So let's start with that 1 milligram of sodium chloride. 1 milligram of sodium chloride. And to get rid of that unit, the milligram, I need to divide by milligram. So there are 1,000 milligrams of sodium chloride and 1 gram of sodium chloride. Okay, so milligrams is gone. Next, I need to get rid of that gram sodium chloride. Gram sodium chloride. Trying to conserve a little bit of space here. G means go to the periodic table, find the molar mass. Molar mass is 58.44 grams. That would be the equivalent of 1 mole of sodium chloride. But I don't need moles, it asks me for volume. That means I need moles sodium chloride here. What do I have? Let's look here. I have 0.14 molar sodium chloride, 0.14 moles of NaCl per 1 liter of NaCl. So we're going to use that as our conversion factor. 0.14 moles of sodium chloride for every 1 liter of sodium chloride. Now let's cancel units. Milligram, milligram, gram, gram, mole, mole. I'm left with liters of sodium chloride, which is exactly what my problem asks for. I'm going to multiply across the top, divide by everything I see at the bottom. I need two significant figures. I get 1.2 times 10 to the negative 4th liters of sodium chloride. It's a really tiny number. Since they gave us a mass in milligrams, I guess we could convert our volume to milliliters, and that would be moving the decimal over 3 places to the right. So right now, if we write our number in ordinary notation, we have 0.00012 liters. Move your decimal 3 places to the right because milligrams are smaller, so we need to make our number bigger. 0.12 milliliters of sodium chloride. Option number 2, we go back and we use the same formula for concentration that we've been using. Moles, liters, plug in what you know, 0.14 molar. I don't have moles, I have milligrams. So you would convert your milligram to moles, and you would solve for liters by rearranging this formula here. To solve for liters, liters is equal to moles divided by concentration. Plug in your numbers and you should get the very same answer, 0.00012 liters or 0.12 milliliters of sodium chloride. You may see the term standard solution. A standard solution is a solution whose concentration is accurately known. Remember, the term accurate means it is very close to the accepted or actual value. Because having the actual or accurate concentration is important, we're going to use a volumetric flask that contains an exact total volume of solution. Same process as before. You take out a massed amount of solute, that's the salt, you put it in your volumetric flask. That's here, step 1. Once you've done that, add a small quantity of water to dissolve. That's B down here at the bottom. Once the solid has dissolved, you continue adding additional water until you reach this line at the very top on the neck of the flask. You put the top on, you shake it, give it one last good swirl, and you've created a standardized solution. I'm not going to work out exercise number 6, but I do want to go over the information that's given and the plan of attack. To analyze the alcohol content of a certain wine, a chemist needs 1 liter, there's volume, of an aqueous 0.2 molar potassium dichromate solution. How much solid potassium dichromate must be weighed? I need how much solid, I need a mass in grams. So if I've got my formula, I'm doing highlighter here. If I have my formula, big M moles liters, I'm going to solve for moles here using 1 liter, and my concentration is 0.200 molar. I'm going to solve for a number of moles, and then I'm going to take my number of moles, the answer, and I'm going to convert it to grams using molar mass. And you should get 58.8 grams of potassium dichromate. You can double check your math and see how well you did. And next up we have the dilution formula. M1V1 is equal to M2V2. We've used this before. You should be fairly good at it. Remember to list your variables, fill in what you know, rearrange, solve for the missing variable, and it's nothing new. Oftentimes when you're asked to dilute a solution, you're using a standard or a stock solution that's already in the closet. And we've done this lab before with that same blue salt solution that you made at the end of the year last year. We also diluted it down, and we're going to talk about how you would dilute a solution. First, the pieces of equipment. A pipette is a device for accurately measuring and transferring a given volume of solution. They come in several varieties. I believe we used a graduated cylinder in our lab, but they look just like this over here on the right hand side. That is a pipette. They're used for measuring exact quantities or volumes. A volumetric or transfer pipette can only measure one given amount, and it'll say what that amount is. Kind of like the volumetric flask can only measure one volume. A volumetric or transfer pipette can only transfer one specific measurement, and it'll say it on the piece of equipment. Generally, you would measure out the quantity of stock solution you determine from the dilution formula given above. So similar to when you were creating a concentrated solution where you take the mass and you'd add it. Well, here we need to know how much of that original solution do I need in order to create this new diluted solution. So we would place that into our volumetric flask. So here we're going to use this transfer pipette. We're going to take the amount of the stock solution that we need, and we're going to solve for that amount using this M1V1 is equal to M2V2 at the top. So you're going to take that amount out of your stock solution. You're going to transfer it to your volumetric flask. Next, you're going to add water to your volumetric flask. That's the final step over here on the right hand side. We're going to add water to that mark on the top of the volumetric flask to reach the desired volume. What volume, here's what I need, of 16 molar sulfuric acid must be used to prepare 1.5 liters of 0.1 molar sulfuric acid. So here's what I have. I have a container. Here's my container. I'm just going to pretend like it's a beaker here. Here's my container. It has 16 molar sulfuric acid. Talk about super concentrated. What I want to do is create 1.5 liters. So I want another container. Here's another container. It's my volumetric flask. Super great artist, I know. I want 1.5 liters of sulfuric acid, but the concentration of this sulfuric acid that I want to make in this container should only be 0.10 molar. So a very, very tiny, tiny concentration of sulfuric acid ions should be floating around in my solution. So what I need to figure out is how much of this solution do I need to use in order to make this new very, very diluted solution. So we're going to list our variables. Concentration 1, volume 1, concentration 2, volume 2. What volume? So there's my question mark of 16 molar sulfuric acid. So how much of this 16 molar sulfuric acid must be used to prepare 1.5 liters? The new volume I'm making is 1.5, and the new concentration that I desire is 0.10 molar sulfuric acid. So if I take my formula, M1V1 is equal to M2V2. I'm solving for volume 1. So if I rearrange to solve for volume 1 is equal to concentration 2 times volume 2 divided by concentration 1. Fill in all of our variables, 0.10 molar, 1.5 liters, and 16 molar. I'm going to cancel like units. My concentration cancels, and I'm left with liters. And if we check, it said what volume of that 16 molar, how much of this do I need to add to make 1.5 liters of that very diluted solution? So you're going to plug into your calculator. And it looks like we need two significant figures. So our answer is 0.0094 liters. But then consider the type of equipment that you're using to make this diluted solution. Do we have equipment that measures in liters? And the answer is no. Our graduated cylinders, our pipettes, our transfer pipettes, our volumetric pipettes, they're all in milliliters. We don't work in really large volumes. So I need to convert my liters to milliliters by moving the decimal over 1, 2, 3 places to the right. So this is equal to 9.4 milliliters. What does this mean? This means I'm going to use a transfer pipette. So let's see if I can draw here. I'm going to use one of those transfer pipettes, and we get, you can use a bulb or a handheld pump, and you are going to remove 9.4, so let me fill this up. You're going to remove 9.4 milliliters of this 16 molar sulfuric acid. You're going to add those 9.4 milliliters of the really concentrated sulfuric acid. You're going to add that to the volumetric flask over here. So here's a volumetric flask. You're going to remove it. You're going to dump those 9.4 milliliters into that volumetric flask. Then you're going to add water to the volumetric flask until the 1.5 liter mark. So this volumetric flask has a total volume of 1.5 liters. After you've added the 9.4 milliliters, you're going to continue adding water until you reach this mark here at the top. Put the stopper on top of the volumetric flask, give it a swirl, and you've created a very diluted solution.